Alright, so I'm planning to make a plotting demo of Lisp in VESC tool. So this is the beta version, the latest one as of today. And if you go to the dev tools in this page, I have rearranged this slightly. So now the tabs down here are on the top. And there is also additional tab, one more tab. So before I had this plot that where you can just select some binding and it will plot it as you go. But now I also have this one. That is one that you can control from the code. Actually, I used to have the same one before. So if you went to real-time data and experiment, you could also do the plotting here. And you can also see that this one is a bit rearranged from before. So they are using the same component right now. I separated out all of this code and put it in a different class, and now you can use it from both places. So let's go back here and just switch on poll data so we see what is going on. And someone was asking if we can make some kind of table where we can have different RPMs for different, different torque limits for different RPMs. And I have a table here. Let's see if I can find it. I can show, by the way, so this is on the VESC package repository. Now I happen to use this table as the example when I made interpolation, but I will just pretend that I'm making this table up as we go now. So let me copy this one. Could also have written it in real time. And the idea here is that we have a table or a list that has small lists in it with 2 elements, and every element shows an RPM value and a power value in percent. So here we say, for example, that at 0 RPM we want to have 80% and at 582 and so on. And I will start by showing just how I would go about plotting this table. So we go to the experiment plot, and then we can do this. By the way, if you go to the readme Lisp, you can go to the plotting and read how these names work, but I will just rely on the auto completion now. They are quite simple. So we do a plot init, and first to give it the x-axis name, and the x-axis in this case is RPM, and the y-axis is power. And then we do plot. Add graph. And I will just call this one linear map, because that's what it would be. And then we do loop for each I, and we loop over int tab. And before we do that, we should also, I think by default it's graph 1, but we should do plot set graph 0. So here we initialize the plot. This will clear everything, and then we add a graph, and when we do add graph after initializing, then the first one we'll add will be graph 0, the next one will be graph 1, and so on. So let's do plot send points. And now the index here, I, since we loop for each in the int tab, will be every row here. And then we can do first to get this one and second to get this one. So first we send the I for the x as the x value, and as the y value we do first of this one and second of this one. Let's give that a try. And now we can see that we got the plot here. So we start at 0 and then we go all the way up to 5000, and these are the different points. I can show some of the controls here too. So here we have history, for example, and what this one does is if I just keep sending data to the plot, it will eventually start erasing them after have this many points here. And then you can also control the different graphs. So now we only have one, and we can switch this one off, and we can also switch the other ones on and off. And we can also do a scatter plot, so you can get a point in every sample of the graph, or we can also have only the points. So, well, this works, But suppose we want to do the map, then we want to have get points in between here. So if we are at 100 RPM, then we want to get the value here, and we actually don't have it in the table, so we want to do some kind of interpolation. And that's something I had used for quite a few times before, and it's simple to do a linear one, but it would be nice to make some kind of smooth curve that connects all of those. And that is what the interpolation library is for, that I added as VESC packages before. So to use it, you just have to make sure in packages that you have done update archive so that you have the latest version, and it should be here. You don't really need to do anything with it here, because as long as you have update archive, you can access everything that is in all of the libraries just from your code here, so you don't need to install anything or so. You just update it, and then you can use the code from the examples. And now we'll show this on GitHub. Actually, this readme here, or the text in here, is generated from the readme, but so far the Markdown support in Qt doesn't do great for code sections. So it's easier to see it if you look on GitHub on this readme page here. So let's try to do some interpolation. All we have to do is import the library and load it. And as you will see in the readme, if you do that, then you will get this ext interpolate extension, and you give it the value that you want to interpolate, and then you give it an interpolation table that is actually compatible with this one, just pairs of values, x and y values. And then you also have an option argument for the interpolation method, and you can, by default it uses Catmull-Rom splines, but you can also use linear, cosine and cubic splines. And if you want to read more about how those work, you can also go to this page here, where it describes some of the math. And I think the tricky part about this one, as a side note, was really to pick the samples from the, in between. So for every point, if you want to do interpolation, say you want to interpolate between those two, you have to give it those points, but you also have to give it points on those lines so that it knows how to make the curve connect smoothly to them when you have those more advanced interpolation methods. And also if you have non-uniform point distribution, you see that this distance here, for example, is not the same as this distance here. So I had to do some sub-interpolation in the code to kind of, when I have this region, I wanted to pick a point here. So, but you don't have to care about that. We can just try to use it. So now we have the interpolation library loaded, and we have the linear thing. And now we can add another graph. And we can call this one interpolated. And then we do roughly the same thing here. And we do graph 1, but instead of looping over all of those points, we want to loop over way more points. So we can just do a regular for loop. And loop from I over, say, we could start a bit before, just to see how it does when we loop pick samples outside of this curve. So we start from -500, and we loop as long as, we could also use a range loop and things, but I think the for loop is easy here, because then I can easily control the step size. So we loop as long as I is less than, say, 6000. That's a bit outside of it. And then the update step in this one will be plus I 10, and then we split it over every 10 RPM, so that should give us 650 different samples. And then you can also see what the speed is of the calculation and plotting, sending the plots and so on. So now we want to, as the x value, send just I as it is. That will be the RPM. And as the y value, we want to send ext interpolate I, and we just give it the interpolation table here. Let's see if that works on the first try. Now I can, before I use the stream shorts command, but now I have to use upload, because when I use upload, then it will actually write this table to the flash memory, and that's how we can load it. If you don't do that, this thing will not exist, because the import is kind of handled by VESC tool. So we do upload, And now we can see the interpolated table here. Actually, after the first upload, you can use stream because it will not erase it in the consecutive uploads. And let's remove the scatter plot. And now we can see that we have a smooth connection between all the points. So that worked easily on the first try. Another thing you can notice here is that when we use extension interpolate, we can just give it any value here, and it will pick the correct point from the graph there. Another thing to notice is also when we send points, it will by default rescale the graph, but we can also switch off the rescaling down here. And now if we do stream again, you can see it update in place. And we could also use this to experiment with the interpolation method. So if we do 0, for example, that should be linear interpolation. And now you see that they're overlapping. 1 is cosine interpolation. This one is rather interesting. It doesn't look nice when you have something like this, but it only relies on 2 points, so it would just put a cosine graph between them, and it will be horizontal in every point. And then you have a cubic interpolation. And you have the default one, which is the Catmull-Round splines. And you could also compare different interpolation methods. So you could, for example, do loop range 0,4 from I to 0,4. And then we do a prog n in this one because we want to do a few things. And this one, we set the graph to I. And actually it will plot this one twice if you do it like this. Yeah, it doesn't matter. And then after setting the graph, we do the for loop in the range loop, and we plot this version. Give it enough parentheses and do some auto indentation with Control I. And we also have to give it more cosine cubic. And I sometimes have been calling Catmull-Rom and sometimes Hermite because I think he refers to it as different things, so we'll call it Hermite this time. And do stream. And that was wrong. Actually, it's surprising it even worked, this one, so because I have 2 indexes to call I. So let's call the second one J actually. The inner loop will be J now. And this will be J, and the last one will be I here. Let's try this. Yeah, and that works now. So now you can see that you have the different graphs here, and you can compare them to each other. You can also drag this one up here a bit. And then now you can see that you can switch off one at a time. And also, by the way, now this one looks the same, but if you do the scatter plot, you see that we have lots of points on it now, so we have all of the interpolated points. And then you can see this is the cosine one, this is the cubic one, and this is the, well, the Catmull-Rom splines, which is very smooth here. Let's do some other experiments. Actually, let me go back to only plot one of them. See if that works. I'm just using Control W to get the graphs now. And you have to activate it too. So now we have the plot again. And you can also afterwards click on this one to scale it to fit the page here. Another note here is that when we are outside of the range here, you can see that, and it will just keep the last value and make a horizontal line. Same thing up here. And then we can show some other tricks. So suppose that, let's see, we could move these points a bit. The one at 500, let's move it over to, say, 800 or so it will be a bit steeper here. So let's do 800. Control W. And now we can see one thing that happens here. For example, we see that it will make a connection that goes like this, so it will undershoot a bit here. And suppose we don't want that. Suppose we want to be a bit more tucked onto this graph here, so we could add another point here. And by the way, this one assumes that these are sorted according to the first one, and I will show first what happens if they're not sorted. Or first I will show what happens what they are. So here we are at 450. Maybe we want to have one at 450 that is roughly 81.125. So that will be in between here. Now you can see that it will follow this one a bit more tighter here and then make this arc here, so you can add points in between to kind of tuck it down against the graph where I need to. The other thing I want to show is, suppose you would add this one at the end here. Now they will not be ordered anymore, and now if we plot it, then actually the first graph plotted correct here because that's how the graph works, but it will, this one will be outside of the graph somewhere. It actually looks decent still, but sometimes when you do that it will, there's even some character here. Sometimes when you do that it will just not look good. So what we want to do then is to sort them, and you could actually in place here, which is quite interesting, you could add a sort here. This, by the way, is something that you could look up in the documentation too. So if you go to the README and we do sort, then you can see that there's a simple sorting function that you give it a function to compare elements, and you give it a list. And this is a very slow sorting function, by the way, but it doesn't matter here because we only sort it when we initialize this thing. And now we already have the second one, which is, let's see, one parenthesis missing, the second argument, which is the list we want to sort. And now we want to make a sorting function, and we can just make a lambda function here. So a function that takes A and B and compares them. And then in this function we want to return, let's see, we want to sort them by the first thing of A and B, and each one of A and B will be a line here. So we can do less than first A, first B. I think this should work. And now if we run the code, yeah, so now we got the list sorted here. And we could also, just for fun, sort it backwards. That will probably, yeah, the interpolation didn't like that at all, obviously. So yeah, now that you have the sorting function, and if you don't feel like just finding where you want to add them, and you just want to add new points wherever you find a reason to add one. Suppose I want to add a point here that goes down a bit at 2000 at say 85, so we get a steep thing like this and up again. Then we can just do another point here, 2000, and we do 85 here. Run it again, and now you got this thing here. So that is the demo of the interpolation. Now suppose we want to update the a demo of the interpolation and the plotting. So now suppose we want to update the power limit based on the interpolated value of this table, and then we can go to config, and you can see that we have all of these things we can change, and there is one that is called current min scale. So we can scale the or current max scale. We can scale the maximum current limit between 0 and 1. And we can use conf_set to do that. And when you do that, you can do this while the motor is running. You can only when you do const_store it will write the flash, and you have to stop the motor. So conf_set is actually quite fast, so you can do this at a relatively high rate. So I will just comment this code out, the plotting, because if you run this later you probably don't want to send the plot points every time you start your program. And then we can just do loop while true, and then we do a prog n, and here we can do conf_set and this one. And now we want to do interpolation. You can just copy this one and use the default interpolation, which is the same as 3 actually. And for I we do get RPM. So, and actually we can do the absolute value of that in case we get a negative RPM. And the next thing to think about is that, well, we have written those in percentages, and this one will take a value between 0 and 1, so we have to divide all of this by 100 or multiply it by 0.01. So that should do the trick. Also do some indentation. And we don't want to run this at full speed because that will just waste a lot of CPU, so we do sleep 0.01. So now it will run at 100 Hz because we sleep 10 milliseconds in every iteration. So let's do stream. And you can see that running this at 100 Hz, the interpolation takes about 2% CPU, so you can run it much faster. So this is a really fast implementation, even though it uses the table in the extension and iterates over the table, which is or the list, which is a linked list. But that is actually fairly fast to do in extensions in C. So let's see if that works. We can actually, I don't have a motor connector now, but if you go to general and current, you see that we have those override limits. And if you just read the config, you can see that we are at 80% now because the RPM is at 0. So it seems to work here at least. I wonder if I just run it without the motor connected, if something happens to the RPM. Let's see. Yeah, it thinks it has some kind of RPM now. Maybe we can even run RPM control. Yeah, surprisingly we can, so even though no motor is connected. Yeah, it's not stable on all of them, unsurprisingly. Yeah, but we should at least, if you read it now, see it change a bit forth and back. Yeah, so we can see that we scale it according to the RPM. So I think that is working. I would just pause and try it with the motor just in case, because maybe this thing was messing with it. Okay, motor plugged in. We just read the default settings. Yeah, the code messed with this one now, but that's okay. And run a detection. Apply and write. And now we can try if this works. I will just do some duty cycle control. Didn't like to start the duty cycle control. Okay, now it's going. And now if we look at the RPM, we see that we are at 4000, and if we slow it down a bit, it goes down. So if you look in the graph and we stay at 4000 RPM, we should be about here. And then we should have, yeah, we should be at 99% almost. So let's see, yeah, 99. Actually, let's change that a bit. Suppose we want to, at 4000, be at, say, 60%. Let's make a big dip in it here. We can also plot it before now. And you see the motor just keeps running while I stream the code now, because it doesn't have to stop it there. So now at 4000 we should be down here and read the code again. And that seems to be the case. So yeah, that is working too. Quite convenient how you can just do the interpolation and update the RPM to any arbitrary table, and it's also easy to do all the plotting for debugging while you do that. And now if you want to keep this one, I would probably comment this code out, and then I would do upload, because then it will stay in Flash, and then every time it boots it will start this code, and then it'll get your RPM map or your power map according to RPM.